Assalamualaikum warahmatullahi wabarakatuh and good morning.
Walaikum salam, Prof. Good morning.
Okay, yesterday we have discussed on the what we call as on the uh, dimensional analysis. Okay, so actually I have improvised this slide. So I have attached or enclosed the the improvised version. Okay, in the WhatsApp group. So you may refer to that notes. Okay. So okay now hopefully you understand on the concept of the dimensional analysis, because throughout uh, the 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 current notes, okay, I will emphasize on the importance of the dimensional analysis, okay, where a lot of researcher has used the dimensional analysis in preparing their charts or graph. Okay. So we have discussed previously on the dynamic loads, okay, on clay and sand. Okay. Now we may look on the behavior of this kind of loads in terms of transient loads, okay, where it's a temporary, where there are changes of the dynamic loads on sample or on the soil of sand and clay. Okay, later on we may discuss on the granular material, okay, which is combinations between sand and clay. Okay. Okay. So on this page, um, behavior of foundation under transient load. Okay. A limited number of laboratory tests for observation of load settlement relationship of foundation under transient load are available. Okay, as far as the author concerns, okay, there are not discussion. A lot of discussion is being made, okay, to look on this transient effect. Okay. Load settlement observation of square model resting on sand and clay and subjected to transient load has been presented by Kani and Sloan. Okay. So this is an example of the transient load where they apply a loads and then they let the loads to sustain for several times. Okay, and then they reduce the number of the loads. Okay, so the model were of varying size from, okay, this is the size of the footing itself, okay, from 114 to 228, and were placed on the surface of the compacted soil layer. Okay, so they apply on sand and clay. Okay, that is led to which the footing was subject of the nature. Okay, the nature of the settlement of footing with time during the application of dynamic loads also shown in the same figure. Okay. So the first one is the first graph is the apply loads. Okay, and at the same time they observe for the settlement uh, during the testing. So in general, during rise time, okay, which is the TR of the dynamic loads, okay, when they increase the load, okay, when the number of the load is start to increase, okay, in this stage, the settlement of the footing increase rapidly. Okay, that is in normal behavior. Okay, so when we increase the load, definitely the settlement will be also increased. Okay, so when the load reach maximum, okay, the rate of settlement will decrease with time. Okay, so relatively they is the load um, here. Okay. In this situation, the load um, in, decrease with time, which is not the number of the load is not have a high increment compared to the previous condition. Okay, however, the total settlement of the footing continue to increase during the dwell time of the loads and reach the maximum value at the end. Sorry, I have a problem with my PowerPoint. Okay. During the dwell time of the loads and reach a maximum value at the end of the dwell time. Okay, during the decay period, the footing rebound to some degree. Okay, this fact show that for a limiting settlement condition, a foundation can support higher loads under dynamic loading condition than those observed from static tests. Okay. So then they come up with the result, okay, which is show that the difference between the dynamic. Okay, this is the dynamic, okay, and this is the static conditions, okay, where they have they monitor the value between the ratio between the dynamic with the static, okay, with uh, different with increment of what we call increment up to 1.2%, 1.5% for sand, and for clay, okay, slightly increase up to 1.2%. Okay, 1.2, sorry, 1.2 difference. Okay, and then Jackson and Handala have recommended the following procedure for that purpose. Okay, so later on, Jackson and Handala has carried out a different study, okay, and to look what would be the difference between the static and also the dynamic. Okay, so for example, if we carry out for the static load, okay, so actually we can predict what will be the behavior under a dynamic conditions. Okay, so they come up with this kind of approach. Okay, so that's why uh, this is the importance of dimensional analysis. Okay, where they produce this kind of what we call as of relations, okay, for S over B, okay, which is a dimensional less, and Q over B square Cu, that is for the static one, okay, while for the dynamic one is QD max, okay, on the dynamic over B square Cu. Okay, so determine the static load versus settlement relationship for foundation from plate bearing test in the field. Okay, so then determine the unconfined compression strength of the soil, which is at the lab. Okay, so when we obtain the result from the unconfined compression strength test, okay, So the QU, normally it is half value for the CU. Okay. So then plot a graph between Q over B square CU. Okay. So the Q is the ultimate load, either static, okay, versus the settlement static over B, okay, over the width of the foundation. Okay, for any given value of static over B, okay, then should multiply with Q over B square CU by the strain rate factor 1.5, okay, and plot it in the same graph. Okay, the resulting graph of static over B versus 1.5 Q over B square CU will be the predicted relation between QD dynamic max over B square CU and S max over B. Okay, so this is the suggestion has been proposed by Jackson and Handela. Okay, so means that they conduct the static testing, okay, at the site, okay, and then by multiplying with the strain rate factor, which is 1.5, okay, for the S over B, so then they assume the behavior for the dynamic, okay, will be 1.5 greater than the static. Okay, so first we plot the graph. Okay, so this is the first procedure. Okay, then we should extend. We get the value of x. Okay, then the extension of x should be 0.5 multiplied with the x. Okay, so the curve, the second curve, okay, which is after extension of 0.5, is the value for the dynamic load. So this is example. If we obtain, if we obtain any result, okay, from the static plate load bearing test, okay, in the stiff clay, and 1.5 meter in diameter are given below. Okay, so that's the information here. Okay, so we have here a B equal to 1.5 meter. Okay. Okay, but the rest is the result. Okay, so in there we have Q, okay, we have S. Okay, now we look on the CU. Okay, so we are provided with the QU. QU equal to 160. Okay, so to obtain the CU, 160 should divide with 2. Okay, so then the CU will equal to 80 kPa. Okay. So later on we need to plot a graph, okay, which is Q over B square CU, okay, versus S over B. Okay. Either we multiply the S over B with certain value, with the value of 1.5, or we just simply multiply the Q over B square times CU with 1.5. Okay. Then we plot the graph. Okay. The graph for QD over max, QD max over BCU is the value, is the pattern for the, what we call it, for the dynamic loads. Okay. So the question asks, okay, we already plot, I have shown how to plot the graph. Okay. Determine the magnitude of the maximum dynamic load that produce a maximum settlement as max of 1.5 meter. Okay. So the first we have plot, I already show how to plot the graph. Okay. So the B is what will be happen if the S max is equal to 0.15. Okay. So this is how could we get the value for the 10%, to estimate the value for the S max at 0.15 meter. Okay. Then 0.5 meter over 1.5 times 100, it show 10%. Okay. So from here, okay, we just draw a line, okay, straight line, horizontal line until it meet the 10%. Okay. So from there, we can estimate the value for the dynamic loads, okay, where QD max is equal to 0.348, one point, actually B square 1.2 times 80. Okay. So to get the value of the QD max, so 0.348 times 1.5 square times 80. So the result for the maximum loading under a dynamic condition is 62.64. Okay. So that is example, okay, for predict settlement, okay, uh, based on the Handala and Jackson approach. Okay. So okay, now we move to another discussion, okay, on the seismic bearing capacity and settlement in granular soil. Okay, okay, the figure show the similarity between the failure mechanism for the static, okay, and this is under earthquake, which is E. Okay, we can notice here the E notation. Okay, so actually we may use the result from the static and then later on could predict what will be the situations if we want to get the value for the bearing capacity and settlement, okay, under the earthquake condition for the granular soil. Okay. So according to this theory, the ultimate capacity for continuous foundation in granular soil are okay. So in this example, okay, the author concentrate on continuous foundation. Okay. What does it mean with continuous foundation? It is a strip foundation or strip footing. Okay, for example, we have a footing, okay, where the length of the footing is relatively too long compared to the B. Okay, so in that case, we consider the footing is under continuous conditions. Okay, so this is the formula, okay, based on Meyerhof, okay, for the static. Okay, so why this is the slightly improvised formula for the earthquake conditions. Okay, in here, uh, we may use all the information from the static condition and then we may multiply with certain coefficients, okay, to get the value for the earthquake condition. Okay, so this is the common bearing capacity factor, okay, in table 6.4. Okay. So you may use whatever approach either from Terzaghi, Meyerhof, okay, to determine the NQ and N gamma, but need to be consistent. Okay, for example, if you use Terzaghi formula, so you need to use the Terzaghi bearing capacity factor. Okay, if you use the Meyerhof, so you should use the Meyerhof bearing capacity factor. Okay. So then they introduce one coefficient, okay, which is to include the horizontal coefficient of acceleration due to an earthquake and also the vertical coefficient of acceleration due to an earthquake. Okay, so the tangent theta equal to kh over 1 minus kv. Okay, so for example, for nq and n gamma, we may refer to the phi value. Okay, but for the nqe and n gamma e, we may refer to phi and also tangent theta value. Okay. So this is either we want to use this table to obtain the NQ and gamma, or we may use this table, okay, to obtain the NQ and N gamma, where we may base on the phi value. Okay. So to determine the N gamma E, okay, or NQE, so we may use this what we call as this graph. Okay, but the result is in ratio, okay, which is N gamma E over N gamma, NQE over NQ. Okay. Before that, we need to determine the tangent theta value. Okay, so the tangent theta value, okay, normally the KH and KV will be provided. Okay, most probably they obtain from the what we call as from uh, the the properties of the behavior of the soil, uh, the the engineering characteristic of the soil. So for example, we have calculated the tangent theta, okay, then uh, with different phi value, okay, here, so the solid line will represent N gamma E over N gamma, while the dashed line will represent NQE over NQ. Okay. So in this case, the range of the phi value, okay, cover from 10 to 40, okay, for both cases. Okay. So the variation of NQ and N gamma with phi are shown in figure 610. Okay, so we'll refer this as a 610. Okay. Figures 611, 6.11, okay, show the variation of N gamma E and N gamma and NQE over NQ with tangent theta and the soil angle phi based on this analysis. Okay. So under static condition, bearing capacity can lead to a substantial substantial sudden downward movement of the foundation. However, bearing capacity related settlement inadequate is important, and it takes place when the ratio tangent theta reach the critical value. Okay. So for example, if Kv is equal to 0, then Kh over 1 minus Kv should be equal to Kh. Okay, so figure 6.12 show the variation of Kh where Kv is equal to 0 with the factor of safety applied to ultimate bearing capacity with phi and with Tf over B for phi 20 and 40. Okay, so this is example, okay, when the Kv is equal to 0, okay, so we can use this graph, okay, to determine what will be the KH. Okay. For example, if we assume the factor safety is equal to 3, okay, so we have two type of phi value, either 30 or 40. Okay. So then the ratio between the depth over B are also provided. Okay. let's say if the soil is replaced on the top of the foundations, okay, on the top of the ground. So definitely the D over B is equal to 0. Okay, where the what we call it, the foundation is not um, put it um, below the ground surface. Okay, okay, or we can use this kind of graph. Okay, 6.5. Okay, to determine the KH value. Okay, so this will be another approach. Okay, okay. So that is for the bearing capacity. Okay, so sorry. For this case, this is for the settlement. Sorry, okay, this is for settlement. Okay, so for the settlement of street foundation due to earthquake using sliding block approach can be estimated, okay, by using the equation of 6.28. Okay, so the previous one is we discussed on the bearing capacity for the granular soil. Okay, now by refer to equation 6.28, okay, we can estimate the value for the settlement under uh, earthquake condition for the granular soil. Okay, so the V is equal to peak velocity. Okay, A is equal to acceleration's coefficient for the design earthquake, while G is acceleration due to the gravity. Okay, 9.81. Okay, the value of KH and alpha AE can be obtained from 6.12 and table 6.5 respectively. These attributes can be used to design footing based on limiting seismic settlement. Okay, so the one that we have discussed previously, okay, this is to obtain the KH, and while this is to obtain the A alpha AE, okay, tangent alpha AE. Okay. So now we look on one example, okay, on how to determine the bearing capacity, okay, under an earthquake condition, and then we need to determine uh, what will be the settlement, okay, if the factor safety used as 3. Okay, so for the A, okay, first of all, uh, the information that be given is the phi value is equal to 30. Okay, so the B is equal to 1.2, the DF is equal to 0.9, while the unit weight is equal to 17.6. Okay, so in this case, the KH is provided 0.176, while the KV is 0. Okay, so to begin with, okay, we need to list the value for the NQ and N gamma first. Okay, so for phi equal to 30, so your NQ and gamma is equal to 16.51 and 23.76. Okay, from there, you may calculate the tangent phi value, tangent theta value, okay, which is equal to 0.176. Okay, so then you need to determine what will be the N gamma E and N gamma. Okay. To get the value for the N gamma E and N gamma, N gamma E and NQ gamma, and NQE. Okay. So you may refer to the table figure 6.11. So you may refer to this table. Okay. So the N gamma is equal to and the ratio between n gamma e and n gamma is 0.4, okay, while the ratio between nqe and nq is 0.63. Okay, so your phi value is equal to 30. Okay. So by using the equation, by using by referring to figure 6.11, so the ratio between n gamma e is 0, n gamma e over n gamma is 0.4, and nqe and nq is equal to 0.63. Okay, so from there you can get the value for the n gamma e and nqe. Okay, so okay, for example, the value of the tangent theta is equal to 0.176. Okay, 0.176. So you may draw a line, okay, 0.1, for example, this is oh, sorry. You may draw a straight line, okay, until it reach the phi equal to 30, okay. For example, this is phi equal to 30, and also phi equal to 30 for nqe over e. Okay. So you may have a two value. First for the nqe, n gamma e over n gamma, and second nqe over nq. Okay. Okay, then you may use the equation, okay, from Tezagi, from the Tezagi, okay, and the equations may include the new notation of n gamma e and nqe. Okay, so the result is about 265.6. Okay, so that is for the bearing capacity value. Okay, so now we may calculate for the settlement. Okay, if the design of the earthquake parameter is V equal to 0.4 meter per second and A 0.32, okay, the settlement, what will be the settlement? By using factor safety 3. Okay, so we may use this equation. Okay, we have been provided with several information. Okay, uh, the one that we need to determine is the KH and also the tangent alpha AE. Okay. So to determine the KH and tangent alpha AE, so we may refer to this 6.12 and 6.5 table. Okay, so the ratio between depth of the footing over the width of the footing is equal to 0.75. Okay, so then we need to refer to this graph, okay, where the phi is equal to 30. Okay, so with the factor safety of 3, okay, so we draw a vertical line until it reaches the solid line, which is represent 0.75. Okay, so if we have two uh, range between 1 and 0.5, so 0.75 is approximately between between both 1 and 0.5 graph. So from there, we draw a horizontal line until we obtain the KH value. Okay. So that is for the KH. Is on the safety factor value. Okay. Then for the alpha AE, so once we have obtained the KH, so we may look on this table, on the table 6.5, okay, to get the value for the tangent AE for phi equal to 30. Okay. So the result for KH is 0.26 and the result for the alpha AE is 0.92. Okay. So put all the information inside the equation 6.28, okay, and then do the calculation. So at the end, the settlement in granular soil approximately 18.7 millimeter. Okay. So that is for the uh, discussion for the bearing capacity and settlement in granular soil under a seismic conditions. Okay. So I have complete for this chapter 2. Okay. Now we may move to the chapter 3, which is on the lateral stress. Okay. So we move on the lateral stress. Okay, lateral earth pressure on retaining walls. Okay. Sure. So in this chapter, we may discuss on how to determine the lateral earth pressure, okay, under an earthquake conditions. Okay. But definitely, we still need to rely on the static uh, lateral earth pressure uh, theory, okay, which is based on column or Rankine, okay, because there will uh, several researchers has improvised. Okay, we may use first approach by Okabe, okay, and the second approach based on the Kuhlmann methods. Okay. So the increase of lateral earth pressure during earthquake induced sliding and or tilting to the retaining structure. Okay. So the majority of case histories of failure reported in the literature until now concern waterfront structures such as quay walls and bridge embankment. Okay. So especially in Japan, okay, so they found out the main problems, okay, with this lateral earth structure, okay, is happen, okay, on the bridge embankment and also on the structure where they built a harbor, okay, or port, okay, which is a quay wall. Okay, they call it a quay wall. Okay. Some of the example of the failure and lateral movement of queen walls due to earthquake are given in page in tables 8.1. Okay, so I have listed all the problems which is related to the queen wall. Okay, so this is the structure that uh, I'm referring to. Okay, where they built a wall. Okay, at the harbor, okay, or the port, which is allowed for the ship to uh, loading or unload the container, okay, where they can reach nearby to the port. Okay, so they have list a lot of failure, okay, on the quay wall during the earthquake. So now we may learn on how to estimate or determine the lateral earth pressure, okay, by including the factor of the dynamic loads. Okay. So Sid and Whitman have suggested that some of these failure may have been due to several reasons. Okay. So such as increase of lateral earth pressure behind the wall, okay, reduction of water pressure at the front of the wall. Okay. So and the last one is the liquefaction of the backfill material. Okay. So this is the three example, okay, which is happened during the earthquake event. Okay, a comprehensive review on the dynamic lateral earth pressure studies conclude that the theory can be divided into three broad categories. Okay, so in order to analyze all the lateral earth pressure during the earthquake, okay, so they have listed three uh, proposed approach. Okay, the first one is the fully plastic, okay, which is based on the static solution. Okay, the second one is solution based on elastic wave theory. Okay, and the third one is solution based on elastoplastic and nonlinear theory. Okay, however, okay, the author has suggested, okay, due to the complex source structure interaction, okay, during the earthquake, the lateral earth pressure theory based on the fully plastic solution, okay, also known as pseudostatic methods, which is widely used by most of the design engineer in detail in this chapter. Okay, so they have choose the first one, okay, to be discussed, okay, in our chapter. Okay, so the number 2 and number 3 most probably, okay, it is more easy to understand or easy to be solved, okay, if we are using any numerical formulations, okay, or numerical software. So in earthquake engineering, to analyze the seismic response of the soil environment and slope, simply adding a permanent body force represent the earthquake shaking to a static limit equilibrium analysis. Okay, so this is the author has also added that to simply to do the calculations, okay, it is better to use the static limit equilibrium analysis. Okay. So we may discuss a little bit on the on the static approach, okay, and then later on we will include uh, the approach based on the dynamic loading. Okay. So analysis and determination of lateral earth pressure are necessary to design retaining wall or retaining structure. Okay. So there are three categories of earth pressure. Okay. The first one is the earth pressure at rest. Okay. So in this case, there will be no movement okay, that we consider for the what we call as for the retaining structure for whatever structure that restrain uh, the soil. Okay, so in this case, they assume that elastic equilibrium with no lateral strain taking place. Okay, which means that the soil has not able to move or to push any structure, okay, in front of it. Okay, so it means that it is at rest conditions. Okay, however, in design, okay, we should assume that there will be a possibility of the soil, okay, to push or to expand or compress, okay, where we discuss as a active and passive earth pressure. Okay, so for example, for the active earth pressure, the condition is under plastic equilibrium with lateral expansion taking place. Okay, while for the passive, with lateral compression taking place. Okay, so this is an example, okay, where the condition at rest, okay, where the soil behave in a stable condition. Okay, while when we discuss on the active, okay, the soil have tendency to be expand. Okay, and for the passive part, normally happen at the lower level of soil, okay, where the soil start to compress. Okay, so this is the three common conditions, okay, when we discuss on lateral earth pressure. Okay. So the important thing is we may determine what is the effective vertical stress. Okay, so a simple explanations. Okay, uh, we need to know what is the unit weight. Okay, and then we need to know what will be the depth. Okay, which is Z. Okay, so to get the value for the uh, effective vertical stress, gamma times Z is equal to effective vertical stress. Okay, so to obtain the value for the lateral stress, the value for the vertical effective stress should be multiplied with the coefficients of at rest, coefficients of active, coefficient of passive. Okay, so for example, at rest, uh, the formula is K naught equal to 1 sine phi value. Okay, and Kp, Ka we may discuss later on. Okay, so for the active and passive, we have two types of theory, which is based on the Rankine and column theory. Okay. So due to the design is more related to active and passive. Okay, so our discussion will be emphasized on active and passive only. Okay, so in Rankine and column, they have made two different. They have made their own assumption. Okay, where for the Rankine, they assume that no additions or friction between wall and soil, okay, which is assumed that wall is smooth. Okay, while the column assume that the failure occurs in the front of the wedge and that friction occur between the wall and soil. Okay. So for the column, okay, they assume there are friction between wall and soil. Okay. Okay, this example, a failure for a one or single layer of soil. Single layer of soil. Okay. Failure is assumed to occur in the form of sliding wedge along a failure plane. Okay. So this is the type of the failure, which is they assume it is under a sliding wedge patterns. Okay. And the direction of the resultant pressure is parallel to the backfill and at 1.3 from the wall base. Okay. So can be used for cohesiveness and cohesion material. Okay. So that is for the Rankine and the column theory. Okay. So how they obtain 1.3? Okay. For example, if we draw a distribution pressure, okay, so the soil, the stress level will be increased with depth. Okay. So by using the concept of moment, okay, if this is the our reference, okay, so the moment arm for a triangle shapes, okay, will be equal to 1 over 3 from the height of the wall, from the total height of the wall. Okay. So that's why they mention them the resultant pressure is parallel to the backfill. Okay, and add to 1.3, 1 over 3 from the wall base. Okay. But this is only apply for a single layer of soil. Okay. For example, if a multi-layer of soil, so we need to use a different approach, which is I not discussed in this chapter. Okay. So this is the equations derived by column for the static approach. Okay. Okay. Due to the situations for the single layer of soil, okay, so they come up with this kind of equations. Okay. So the coefficients of active, okay, has been derived based on this formula. Okay. So what is the important things that we need to know or to be included? First is the phi value. Okay. The phi value is obtained from the soil properties. Okay. And for example, if the retaining structure is designed in 90-degree, so the beta value will be equal to 0. So, but in this case, the sample or the what we call as the structure is being built in 90-degree towards the ground. Okay, so we need to measure the value of the beta, okay, based on the vertical axis or y-axis. Okay, so then we have here angle angle of frictions. Okay, sorry, angle of friction between wall and soil. Okay, so the delta. Normally the delta is less than phi value and it around 2 over 3 or 2/3 from the phi value. Okay, so it could not greater than phi value. For example, if the question doesn't provide any delta value, so we can estimate the value of the delta is around 2/3 from the phi. Okay. The last thing is the I. Okay, I is the slope of the backfill with respect to the horizontal. Okay, so for example, if if the area or if the backfill has have a flat surface, so your I should be equal to 0. Okay, so if the I has certain degree, so we need to determine what is the I value. Okay, so that is for the KA. So the rest is the H value, is the height of the retaining structure. Okay, gamma is the unit weight of the soil. Then we can calculate what will be the PA. Okay, so actually, this part is referred to the effective vertical stress. Okay, okay. I will show you how this equation obtained. Okay. So, okay, for example, okay, this is our retaining structure. Okay. Then we plot the distribution diagram, the distribution pressure diagram. Okay. So from the top, okay, we assume that effective vertical stress is equal to 0. Okay, because there are no surcharge on the top. Okay, so then the value will increase, okay, which is the vertical effective stress equal to unit weight time height of the structure, or the retaining wall, okay, or the ground. Okay. So this is the distribution diagrams. Okay, distribution pressure diagrams. Okay. So when we want to get the value for the loads, okay, so we need to calculate the area. Okay, so for this case, it is a triangular shape. Okay, so 1/2 multiply with the height. Okay, this is the height, and multiply with the value of the x-axis, which is unit weight time h. Okay, because this is unit weight time h. So at the end, the value is equal to half times unit weight time h square. Okay, so this is in this is in what we call vertical direction. Then to change into lateral, we may multiply with the Ka. Okay, so from there we obtain the loads for the lateral, which is Pa. Okay, so that's why this equation only suitable for single layer. So I will not discuss on multi-layer type of material. Okay. So in the actual design of retaining wall, the value of the wall frictions delta is assumed to be half phi or two-third phi value. Okay. So if the delta is not provided, so you may use these assumptions. Okay. So the active earth pressure coefficient for varies phi value. Okay. Okay. The active earth pressure coefficient for varies phi, I, and beta with delta two-third are given in table 8.3. Okay. Okay. For example, for this case, okay, if we refer to table 8.2, okay, so if we want to determine the KA, okay, so we need to rely on this information, okay. For example, if the beta is equal to 0 and I is equal to 0, okay, so we can estimate the KA value based on the what we call on the uh, coefficient of phi, okay, but the value for the delta should be 2/3 of phi, okay. Uh, the rules, okay, to use the table 8.2, okay. So for example, if the value of the delta is not 2/3 of phi, so definitely we may use this equation, okay. So what does it mean beta is equal to 0? Means that the construction of the retaining wall is 90°, okay, and I is equal to 0 when the backfill is uh, flat, okay. There are no slope on the top of the backfill, okay. Okay. So for this case, okay, there are several combinations between I, okay, beta, okay, and 2/3 over phi, okay, should be used, okay, to obtain the Ka. Okay, so the Ka for this case we have values of I, beta, phi, and the delta should be 2/3 of phi. Okay, so that is for the to use the chart. Otherwise, we may calculate using the manual, using the equations. Okay, so that is for the static. Okay, so now how could we determine the dynamic uh, lateral stress effect? Okay, so the equation of the column has been improvised by this researcher Mononobe Okabe, okay, to determine the value for the effect of the dynamic types. Okay, so the column active earth pressure equation can be modified to take into account the vertical and horizontal coefficient of accelerations induced by an earthquake. Okay, this is generally referred to as the Mononobe Okabe analysis. Okay, so the Mononobe Okabe solution is based on the following assumptions. Okay, I guess most of the assumption is similar with what has been assumed by column itself. Okay, so the failure in the saw takes place along a plane such as PC shown in figure 8.2. Okay, so figure 8.2 what we have discussed previously. Sorry, this figure. Sorry. This figure, okay, 8.2. Same with what we have discussed on 8.1 previously. Okay, this one. The movement of the wall is sufficient to produce minimum active pressure. Okay. So for this case, we try to solve the active problems. The shear strength of the dry cohesion soil can be given by the equation. Okay, so this is the equation to represent the shear strength. Okay. At failure, full shear strength along the failure plane is mobilized. Okay. The soil behind the retaining wall behave as a rigid body. Okay, so that is the assumption has been made by Mononobe Okabe, which is similar with what has been made by column. Okay. So the difference is the modern combat has introduced KH and KV. Okay. So and then after introduce the KH and KV, there will be a slightly difference in terms of the force of polygon. Okay, they call it as a force of polygon. For example, for a normal column approach, so the force of polygon will be like this one. Okay, P W F. Okay, so when they introduce the KH and KV, so they will include these um, notations. Okay, or on the polygon force. Okay, by introducing the new KV times W and KH times W, okay, to represent the action of accelerations. Okay, so okay, the force on the force of on the failure which per unit width of the unit length of the wall width of the wedge W. Okay, so the active force, which is the same that we have discussed previously, but this case is related to the earthquake, which is PA. E is the earthquake. Resultant of shear and normal force along the failure plane, which is the W. Okay, and the initial force, which is in horizontal and vertical direction. Okay, where the KH and KV is obtained from the uh, horizontal component of earthquake acceleration and vertical component of earthquake the acceleration. Okay, and the G is acceleration due to the gravity. Okay, so this is example. This is what we had discussed previously. Okay, so by introducing the KV and KH, so they can comply with the earthquake load. Okay. So the difference between the static is half unit weight H and KA. Okay. So this is on the earthquake where they introduce 1 minus KV. Okay. And the KA is slightly different with the one that we use in the what we call as in the static. Okay. So you may refer to the static formula and compare with the KAE. I guess he introduced the delta. Okay. So they include the delta. Okay. So all this has been improvised by include the delta for the static one. Okay. So we have familiar with KH value over KV. Okay. I guess this is the same approach that has been uh, proposed by Jackson and Hadala on the shallow foundations. Okay. Which is tangent KH over 1 minus KV. Okay. So for the active force condition, PAE, the angle alpha that the soil which ABC located behind the retaining wall mixed with the horizontal table issued in figure 8.3. Okay. Table 8.4 give the value of Ka for various phi delta I KH. Okay, so this is a simplified methods to get the value of the KAE. Okay. The best you may use the equation. Okay. So if you want to use the simplified, so you may refer to the table on the next page. Okay. So this is how to determine the KH. So once we determine the KH, so we can determine the value for the KAE by referring to the KV is equal to 0 and beta is equal to 0. Okay. So for example, if the KV is not equal to 0, so we need to use the equation. Okay. The equation of KAE to get the KAE value. Okay. Okay. So this is another consolidation that need to be understand. Okay, considering the active force relation given, the term sine phi minus theta minus I has some important implications. Okay, so for example, if the value is negative, okay, no real solution of KE is possible. Okay, so it means that if the phi is greater than what we call as the sorry, the theta is greater than phi. Okay, so there is no real solutions of KE is possible. Okay, physically it implies that an equilibrium condition will not exist. Hence, for stability. Okay, so therefore we need to understand, okay, in terms of how to have to limit, okay, the slope on the backfield. Okay, to make sure that the sign value not reach a negative. Okay, so your I should less than phi minus theta. Okay, so for example, for no earthquake conditions, okay, which is theta is equal to 0, okay, your I should less than phi. Okay, is that the backfield should not greater than phi value. Okay, under a static or where there are no earthquake condition. Secondly, for the back horizontal backfield, I is equal to 0 for stability. Okay, uh, the phi should greater than the theta. Okay, so we need to choose a very good material. Okay, which is greater than the theta value. Okay, so for example, if we construct a backfield, a flat backfield, okay, so we need to make sure that we compact well, okay, the backfield to make sure that the phi is greater than the theta value. Okay, because the compaction may increase the phi value. Okay, so this is a suggestion where we need to make sure that the negative value should be not should not be obtained. Okay, for this sign. Okay, since okay theta for theta is equal to tangent, okay, kh over k p, for stability combining result in kh over k. Hence, the critical value for the horizontal acceleration can be defined as k. So this is the critical kh value. So from there we can we we, we understand that, okay, this is the critical value should be identified. Okay. Okay. So now we move to how to use the mononomial OKB to determine the KA value. To determine the 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 lateral load under dynamic. Okay. So since the value of KA are available in most standard handbook and textbook, okay, so Arango developed a simple procedure for obtaining the value of KE from the standard chart of KE. Okay, so uh, they have improvised. Arango have improvised the mononobi Okabi. Okay, where still they use the static. Okay, and then they improvise from to be used in the dynamic. Okay, so when we look on the formula, this is the normal. This is the formula for the static. Okay, so then they come up with this uh, equations. Okay, where they introduce as AC. Okay, so the AC is equal to cos square beta. Okay, which is refer to the same Ka value. Okay, but they use the cos there. Okay, and then for the dynamic, okay, so he introduced the AM. Okay, so the AM will be KAE cos theta cos square theta, because in the dynamic we include uh, the theta. Okay, so this is the improvise has been made by Arango. Okay, I will discuss later in our example. So then the I prime is equal to I, which is the backfield, degree plus theta, okay, and B prime is equal to B plus theta, okay. So he has simplified the AM, okay, by using the B prime and I prime, okay. So the preceding equation in is similar to equation 8.13, except for the fact that I, okay, and beta prime are being used, okay, to replace the I and beta. Those is can be seen that, okay, okay, so this is just a simplification approach, okay. So later on, the active earth pressure PAE can now be expressed as PA I prime beta prime times 1 minus kV times P S3. So he has come up with another equation, which is the PS3. Okay, so this is how Arango has improvised the Mononobe Okabe approach. Okay. And then, okay, this is the step on how to use the Mononobe Okabe equation or approach by improvise from the Arango. Okay. So the procedure is calculate the I prime, calculate the B prime, okay, with known value of phi delta I prime B prime. Then we may determine the KA. Okay. From the KA, we can get the value of the PA. Okay. So then we calculate 1 minus KV. Okay. So then calculate S3 P value, okay, which is from this graph. Okay. Okay. Then calculate PA, which is PA I prime B prime times 1 minus kV times P. Okay. So this is referred to the one that we have calculated in this case, okay, because we are using the I prime and B prime. Okay. So this is referred to the procedure of number 5, and the last one is referred to procedure number 6. Okay. So this is the simplifications to get the asterisk P. Okay. Okay. So I provide one example, but we may refer to the procedure on this page. Okay. Okay. So this is an example, okay, on how to use the Mononobe Okabe approach, and has been improvised by Arango. Okay. So the first step is to calculate the I. Okay. I prime and B prime. Okay. Where we can get the I prime and B prime in this page. Okay. Okay. So, okay, refer to figure 8.2. Okay, so this is the figure that we normally that we refer, okay, to solve the problems. Okay, okay. In this case, this is just to identify what is the meaning for each notation. Okay, we have been provided with the beta is equal to 0. Okay, so means that the slope has been construct. Sorry, the wall has been construct 90 degree. Okay, I is equal to 0. So the backfill is also flat. Okay, the phi is equal to 36. Okay, this is the value of the friction angle. Okay, and the friction between wall and soil is 18. Okay, so if 18 is about half, means that delta is half of phi value. Okay, the height is 44.5 and the unit weight is 17.6. Okay, KH and KV is being provided as 0.3 and 0.2 respectively. Determine the active force per unit length of the wall. Okay, so to begin with, we need to determine the theta value. Okay, so the theta is tangent KH over 1 minus KV. So then we obtain 20.56. Okay, so I prime is equal to I plus theta. Okay, in our case, our I is equal to 0 and beta is equal to 0. So I prime and B prime actually is equal to the theta. Okay, so then we use the equation for the KA I prime B prime. Okay, because the B prime has been simplified, which is equal to B plus theta. Okay, then include all the informations inside the KA. Okay, then we have calculated the KA as equal to 0.583. Okay, so that is for the KA. Okay, now to determine the PA, okay, so using the static equation, okay, our PA is equal to half times 70.6 times 4.5 square times 0.583. Okay, which is equal to 103.89. Okay, so that is the PA. So this PA should be multiplied with the asterisk P. Okay, so for the asterisk P is equal to cos square B prime over cos theta cos square P theta. Okay, so the result is 0.966 and 0.9363. Okay, okay. In order to get the result for the PAE, okay, so the PA multiply with the 1 minus KV. So KV is 0.2. Then multiply with 0.963 is 0.9363. So the PAE is equal to 77.81. Okay, so that is for the uh, to calculate for the PAE. Okay, so if you have time, you can estimate what will be the static value. Okay, because the static is equal to half unit weight times H KA. Okay, so you may use the KA based on this uh, equations. Okay, then if I'm not mistaken, the PAE from the static is greater than the PA from the static is greater than PA under the earthquake. Okay, okay. So this is just to study on the effect of various parameter on the value of the earthquake pressure coefficients. Okay, so for example, what would be the effect of the wall friction angle? Okay, based on the finding, they find out that the effect of the wall friction angle on the active earth pressure coefficient is rather small. Okay, for example, if we increase the value of the delta from 0 to 2/3 of the phi, so there will be no significant difference. Okay, in estimating the KAE or the coefficient of KAE. Okay. So what will happen if the soil friction angle, okay, is different? Okay. So in their study, um, it can produce up to 35 degree higher or difference between 30 degree to 45 degree. Okay. So in that sense, we need to make sure that all the data that we obtain or we input should 100% represent the soil properties that we have tested. Okay. Here, the small error in the assumption of the small friction angle could lead to a large error in the estimation of PAE. Okay, for example, uh, we estimate or we use the phi equal to 45, but in reality, when we do a, a triaxial or what we call a shear board test, the value is 30. So 35% difference due to the difference of phi value. Okay. And the last one, what will be the effect of the backfill? Okay. So if I is being increased up to 10, okay, at the early KH or at the KH is equal to 0, so there will be a no slightly big difference. But when the KH start to increase, okay, the value of the difference uh, show show a uh, high difference between uh, 0 to 10 degree of backfill value. Okay, but the most important things on the phi value. Okay, so the phi value is significantly contribute to to the a huge difference of the KAE or PAE value. Okay, okay. So we take a rest and then we may continue at 10:40.